Hello everyone, my name is SJBIT, working as Assistant Professor in the Department of ECE SJBIT. In today's video, I'll be explaining about Module 4, Sampling and Quantization. So before moving on with this, we need to understand why we go for digital representation of analog signals. So in a continuous wave modulation, some parameter of a sinusoidal carrier wave, it is varied accordingly with the message signal. The amplitude and analog forms of continuous wave modulation were originally it was developed in 1900 with analog sources, usually voice and mind. As the understanding of the digital transmission improved over the period of 1930 to 1960s, there came the recognition for the digital transmission, and it has many advantages over the analog transmission. However, it is not till the development of the solid state electronics, microelectronics and large scale integration in 1970s. The first step in the evolution of analog to digital transmission is the conversion of common information sources such as voice and music. So we need to convert an analog information source such as voice, video to digital representation and also its subsequent transmission forms. So this is in contrast to the modern layered approach to communications where the different aspects of the communication process are clearly separated. As a result of this, the nomenclature may be confusing few times. Say for example, pulse code modulation, it describes both a method of digitally representing an analog source and a method for representing the information over a baseband channel. For the purposes of this module, there been a techniques of digitally representing analog sources. So first we'll understand why digitizing of analog sources has to be done. The introduction is that it has several advantages. That is the transmission of digital information over the analog information. So few of the advantages are: first one, digital systems are less sensitive to noise than the analog signals. For long transmission length, the signal may be regenerated effectively, error free at different points along the path, and the original signal transmitted over the remaining length. Second point is, with the digital systems, it is easier to integrate different services, for example, video and the accompanying soundtracks into the same transmission scheme. The third point is the transmission scheme can be relatively independent of the source. For example, a digital transmission scheme that transmits voice at 10 kilobits per second would also be used to transmit computer data at 10 kbps. Fourth point, the circuitry for handling digital signals, it is easier to repeat, and digital circuits are less sensitive to physical effects such as vibration and temperature. Last point is the digital signals are simpler to characterize, and typically they do not have the same amplitude range and variability as the analog signals. So this makes the associated hardware easier to design. While almost all media, say for example cable, radio waves, optical fibers, may be used for either analog or digital transmission. Digital techniques offer strategies for more efficient use of these media. Various media sharing strategies known as multiplexing techniques are also easily implemented with digital transmission strategies. There are techniques for removing the redundancy from digital transmission, so has to minimize the amount of information that has to be transmitted. These techniques fall under the broad classification of source coding. So there are techniques for adding controlled redundancy to a digital transmission, such that the errors that occur during the transmission may be corrected at the receiver without any additional information. As an example, we can have a forward error correcting techniques that is relatively simple by today's standard and can also reduce an error rate of 7% at the channel output to as little as 0.001% at the decoder output. Digital techniques makes it easier to simplify complex standards that may be shared on a worldwide basis. So this allows the development of communication component with many different features, and also their interpretation with the different component produced by a different manufacturer. Other channel compensation techniques such as equalization, specially adaptive version, are easier to implement with digital transmission techniques. So it should be emphasized that the majority of these advantages for digital transmission it rely on the availability of low cost microelectronics. Next we'll move on to the first topic, that is the sampling process. So here in the sampling process we'll be studying what do we mean by sampling and how do that happens, what are the different conditions. Much of the material on the representation of signals and systems they use both continuous in time and frequency domain representation. So we will consider the representation of the periodic signal. We see that the Fourier transform of a periodic signal with period T naught consists of infinite sequence of delta functions occurring at integer multiples of the frequency f naught is equal to 1 over T naught. On the basis of this observation, we may state that making a signal periodic in the time domain has the effect of sampling the spectrum of the signal in the frequency domain. So the sampling process it is usually described in time domain. So as such it is an operation that is basic to digital signal processing and digital communication. Though use of the sampling process, an analog signal is converted into a corresponding sequence of samples that are usually spaced uniformly in time. So clearly, for such a procedure to have a practical utility, it is necessary that we choose the sampling rate properly so that the sequence of samples uniquely defines the original analog signals. So let us draw, say suppose this is the message signal and analog signal, and it is instantaneously when it is sampled. Let's say this is g of t. So your g delta of t, it is the samples like this. So suppose that we have a sample signal g of t which is instantaneously sampled at the rate and at a uniform rate, say once every ts seconds. Ts seconds in the sense this period is ts. Consequently, we obtain an infinite sequence of samples which is spaced ts seconds apart, which we denote by g of nts. So, where n takes all the possible integer values, where ts is the sampling period, fs is equal to 1 over ts, that is the sampling rate. This ideal form of sampling is called as instantaneous sampling. So let g delta of t denote the signal obtained by individually weighing the elements of a periodic sequence of Dirac delta function, which is spaced ts seconds apart. So g delta of s, g delta of t, it is given by summation n is from minus infinity to plus infinity g of nts into delta of t minus nts, where g delta of t, it is the ideal sample signal. The term delta of t minus nts, it represents a delta function which is positioned at time t is equal to nts. From the definition of the delta function, we can recall that the idealized function has a unit area. So we may therefore view the multiplying factor g of nts as a mass assigned to the delta function. So a delta function weighed in this manner, it is closely approximated to the rectangular duration delta t and amplitude g of nts by delta t. If we make delta t smaller, better will be the approximation. So the ideal sampled signal g delta of t, it will be having a mathematical form which is similar to that of the Fourier transform of a periodic signal. So applying the Fourier transform, we get g delta of f, or you can write like this: g delta of f is equal to summation n is from minus infinity to infinity g of nts into exponential of minus j 2 pi f ts. So this is the relation we call it as discrete time Fourier transform. So it may be viewed as a complex Fourier series representation of the periodic function g delta of f with the sequence of samples g of nts. So this relation we call it as the discrete time Fourier transform. So we can apply the series of Fourier transforms and its relations to obtain the proper sampling. So the final equation is g of t is equal to summation n is from minus infinity to plus infinity g of n divided by 2w into sinc function of 2Wt minus n. So this provides an interpolation formula for reconstructing the original signal g of t from the sequence of samples g of n divided by 2w. With the sinc function, we are using the interpolation function. So we may now state the sampling theorem for a strictly band limited signals of finite energy in two equivalent parts. One is a band limited signal for finite energy, which has only the frequency components less than W hertz, and it is completely described by specifying the values of the signal at instants of time, which is separated by 1 over 2 W seconds. Second point is it's a band limited signal of finite energy which only has frequency components less than W hertz, may be completely recovered from a knowledge of its samples taken at the rate of 2W samples per second. The sampling rate of 2W samples per second for a signal bandwidth of W hertz is called the Nyquist rate. It is reciprocal of 1 over 2W and it is called the Nyquist interval. The derivation of the sampling theorem, it is based on the assumption that the signal g of t is strictly band limited. In practice, however, an information bearing signal is not strictly band limited. With the results of some degree, consequently, some aliasing is produced by the sampling process. Aliasing refers to the phenomenon of a high frequency component in the spectrum of the signal seeming takingly on identity of a low frequency in the spectrum of its sampled version. Aliasing in the sense, so overlapping like this. So this part we say it is a aliasing part. To combat the effect of aliasing in practice, we may use two corrective measures. One is prior to sampling, a low pass pre alias filter is used to attenuate those high frequency components of the signal that are not essential to the information being conveyed by the signal. Second is the filtered signal is sampled at a rate slightly higher than the Nyquist criteria. So the use of sampling rate higher than the Nyquist criteria also has the beneficial effect of easing the design of the reconstruction filter used to recover the original signal from its sampled version. The reconstruction filter, it is a low pass with a pass band extending from minus W to plus W, which is itself determined by the pre-alias filter. The filter will have a transition band extending from W to Fs minus W, where Fs is the sampling rate. The fact that the reconstruction filter has a well-defined transition band means that it is physically realizable. So this is compared to the implementation of ideal reconstruction filter corresponding to sinc function that would be necessary if the signal was not overlapped. So you can see that aliasing effect is nullified. So in the video I have started with the sampling, why digitization has to be done, why analog signals are converted to digital signal, what are its advantages, why are we shifting to the digitization, and then the process of shifting analog to digital signal, that is sampling. In depth we have discussed about the sampling process. So in my next lecture I'll be explaining about PAM, that is pulse amplitude modulation. In detail I'll be explaining about the PAM, how do we get the pulse amplitude modulated signal. Thank you.